Going into the hash computation stage of the SHA-256 implementation, which is given by Chapter 6.2.2 of the NIST specification, the hash computation stage processes each of the 512-bit message blocks returned by the preprocessing stage, and for each 512-bit message block, first creates a message schedule with 64 elements, where the first 16 elements are the 16 32-bit integer values prepared by the preprocessing stage, and the remaining 48 elements are a function of previous elements in the message schedule transformed by two functions named small sigma 1 and small sigma 0 by the specification. Small sigma 1 is defined in Chapter 4.1.2, which makes clear that small sigma 1 is a triple XOR over two right rotation functions and a right shift function. The right rotation function is defined in Chapter 3.2, Section 4, and is a circular shift rotation of the bits in the given value to the right by a given number of positions. A formula for this is presented and can be replicated in Python, where care needs to be taken to keep the resulting value within 32 bits. The right shift function is defined in Chapter 3.2, Section 3, and is really just a right shift of the bits in the given value to the right. This is a built-in function in Python, so the implementation of this function was simple. With this, small sigma 1 was implemented, and small sigma 0, also defined in Chapter 4.1.2, was quick to implement, as small sigma 0 is also just a triple XOR over right rotations and right shifts that were now readily available to use. Going back to the hash computation stage, the next functions to implement were found in the shuffle step of the hash computation, where the current working variables containing the current hash value are mixed and augmented with various functions such as large sigma 1. Like small sigma 1, also large sigma 1 is defined in Chapter 4.1.2 and is this time a triple XOR over just the right rotation function, which was already available and with which large sigma 1 was quick to implement. Same story for large sigma 0, also defined in Chapter 4.1.2, which again was a triple XOR over the right rotation function and as such quick to implement as well. The ch function is defined in Chapter 4.1.2 and is this time a choice function where x chooses if the result is y or z. The formula presented I could translate straight into Python and proceed to implement the majority function, returning the majority bit among 3 bits, and the formula presented could be translated straight into Python as well. The last piece left to implement was K256, which is defined in Chapter 4.2.2 and which is just a constant lookup table of 64 32-bit integer values. This table is presented in specification and can be copied straight into code, but to turn this into the final lookup table, first required to convert the presented hex byte strings into 32-bit integer words. Once this K256 lookup table was implemented, the hash computation stage was complete, and with it, the overall implementation of SHA-256 was complete as well. Going back to run the driver on the two NIST-based test vectors and the third custom test vector, then showed that this implementation now successfully computed all expected SHA-256 hash values, which was great to see. Verifying that this would indeed be a full implementation of SHA-256 would of course require to run the implementation of all of the provided NIST vectors, but for starters, the successful execution of the three test vectors chosen did it to conclude this educational demo implementation of SHA-256.